YouTube channel. Here is another following video will be another chapter for Form 4 Chapter 4 Heat, where in this video I'm going to show you on specific latent heat. We'll cover specific latent heat, heating curve, cooling curve, followed by the three gas law. Now to start off with, if this is the first time you're viewing this, I have a series of Form 4 additional maths syllabus as well as Form 5 additional maths, and I'm also currently doing the Form 4 physics or Form 4. And once I've finished with Form 4 Chapter 5, then I shall start Form 5 physics. Now to start with what we have, to show you what we have gone through in my previous video. As for recap, because I would normally advise students to always spend almost a week for every video watch to read through your reference text. Also try to do those objective questions over 1 week time. So previously we have gone through the concept we have given to us in the previous video. This is on law of conservation of energy, which is the first law of thermodynamics, where energy transforms from one to another, from kinetic to heat, from potential gravity energy to heat, or from electrical energy to heat. Okay, then one example you may use in your objective question, depends on what parameter used. Be sure you are using SI unit. Electric energy, power in watt. Power in watt. How many watt used to heat up water for how long, how many seconds. And then M is in kg, C is a constant, then temperature is in degrees C. Okay, which depends on what the question, what they are asking. Okay, so this is one of example. How do you find the specific heat? Okay, by using this experiment. You shall read on this experiment, and also why the value is higher. Then another example would be transfer of heat, hot water, cold water. The hot water is transferred into the cold water, so the amount of heat loss will be the same as the amount of heat gain by hot water, by cold water, of course. The cold water shall gain heat, where the hot water shall lose heat. Okay, so the amount of heat loss from here to here should be the same. So that's why you have this equation, and the final equation should be always lower than the hot water, but slightly higher than the cold water. That's why you have MC theta. Then also application, how you're going to use it. You need to read on your reference. There are a few more example, but one of it, for you to understand the concept of specific heat capacity. This is where you have the sea breeze and the land breeze. And here it comes today, chapter 4. This is considered to be part 3. In part 3 of the video, previously we have learned specific heat capacity. So this part of the video will cover specific latent heat. Now, in specific latent heat, symbol L is defined as the amount of heat. Q is amount of heat. Q, you've got to make use of this symbol. Q is amount of heat used to change phase of 1 kg of mass. Change phase, it means you change from liquid to gas or solid to liquid. Okay, amount of heat required to change 1 kg of certain material from one phase to another at constant temperature. Okay, so it's different than from what we had last week. The C is specific heat capacity. The C is the amount of heat required to heat up 1 kg per 1 degree. So this is specific heat capacity. Whereas today, or this video, we'll be doing amount of heat to raise 1 kg over a fixed temperature. So the unit for L would be equivalent to amount of heat J, joule per kg at constant temperature. So what is it about? Okay, the concept behind it, where you can find this. Previously is a combination from the previous. So if you have a cube of ice is in solid form, ice cube. Always mistaken with the BM. Shouldn't be worried whether it's a BM English, but ice cube. So the ice cube is in solid phase. Is in solid. The phase is in solid. Okay, meaning if you look at it in the microscope, okay, H2O, H, O, and O, you have one molecule, but the another molecule of the H that would form a bond, stretch out. So it's stretch out. With another bond, fully stretched. That's why you have a solid phase. H and H you cannot have bond. I mean, it's hydrogen bond. Maybe I'll put it this way. I mean, and you have another, maybe here to here, to here. Then you have another bond. Okay, then it bonds out. That's why you have a solid phase. Okay, and what happened when this solid melt? You have a pool of water. This pool of water is in liquid phase. Okay, and then you heat it up further. It would be in, say, gaseous form. It would be vaporized, boiling, simmering, and then boiling, and then it will be in vapor. It's a water, and this vapor defined as a gaseous state or gas phase. Okay, this is liquid phase. This is solid phase. When you look under the microscope, electron microscope, what happened to the molecule of water? They will be different because the molecule will be the same. It's just that the water will be free from each other, Maybe they will still have some small bonding, but maybe this one is bond, but it is free from this molecule. This molecule is not bond to it. H and H. This molecule is not bond, or maybe this molecule is bond to here, and that's why you have a pool of water, because from ice to water, all the bond has been broken off. Right? Broken off. That's why you have a loose. The molecule is loosely being distributed. Okay? And the same goes with vapor. When it's vapor, you break up more of this hydrogen bond. You do not break this bond, O to H bond, but it is the hydrogen bond, okay, that is going to interfere with its state. Okay, so latent heat is actually energy required. Specific latent heat is energy required to change one phase of the 1 kg of material over the same temperature, meaning from ice to pool. So what's the energy required to cut all this bonding so that it will become a liquid phase? And from liquid phase, what's the energy required to be transferred into vapor? So this is where the specific latent heat is involved, meaning you actually cut down the bonding, not the molecule bonding, is between molecule. Okay, the bonding between molecule. You do not cut individual atom. Let's say, for example, from water to vapor, when you boil water, you do not get hydrogen and oxygen. You do not get that. When you boil water, you will still get water because you actually cut the bond between water molecule. You do not cut this bonding. You do not cut it. You do not break this bond. If you break this bond, meaning you are going to get hydrogen and oxygen. There's no way. The energy add into the water while you boil water is insufficient to break this bond, but it is sufficiently to break this bond. Okay, this is called hydrogen bond. It's supposed to be hydrogen and oxygen. Okay, so yeah, so this is the energy, specific heat capacity. It's supposed to be specific latent heat. So specific latent heat, this is the energy used to break intermolecular bond. Okay, so that's the concept, and then how it goes about it. It will be, say for example, previous example. Initially, I'll have this cube of ice. Not one, maybe one glass of it. You have ice in a glass. Okay. So what happened? You have a thermometer. You measure its temperature. In my first video, you put it in, and then your thermometer. It's supposed to be at maybe not 0, but maybe it's so cold that maybe it is initially is at says negative 10 degrees C. Okay. Then what happened? You leave it there in the room, or maybe you put it under a kettle, electrical heating element underneath it. So what happened? A few seconds later, you see they will have some small cube ice floating. So some water, some ice floating on a cup of very cold water. You still get cube ice. What happened now here is you still have your thermometer, but the temperature could read maybe 0 degree. Okay, even if they are, as long as there are still cube ice on it, it should be 0 degree under normal atmosphere. We are not talking about density, because the density is supposed to be at 1 when temperature is about 4 degrees C, but we're not going towards that. But the concept here is when heat it up, or maybe it absorbs the heat from the surrounding, it melts all this ice and turns out into water with a few more small cubes of ice floating. The temperature remain 0. So what happened? You take some time, a few moment later, heat it up further, or maybe you just leave it there. All the ice went missing, and when you have your water. Temperature remains, otherwise you can tell temperature, isn't it? Maybe the temperature reach up to 30 degrees C. It's pretty hot in Malaysia, depending on which month, yeah. But normally it's about 27, but it could reach up to as high as 30 degree. Okay, so what happened at 30 degree? Well, this time now you want to heat it up further. Your Bunsen burner. Of course, you have the match. Okay, the wire mesh with a red hot lake on it. Okay, well, okay, I didn't draw it, but it's there. Okay, heat it up. It won't go up straight away, but it will wait for some time, and then you have your water. Also, your thermometer. Okay, this is a thermometer. It's supposed to be not have this color, but I'm supposed to draw a thermometer first. Only then I will draw this scale. Okay, then I heat it up. Maybe reach up to maybe 60 degrees. Okay, or maybe 60 degrees. Okay, and so on. Okay, so this is how it goes from here to here, from here to here, and to here, to here, right? And then what happened is it takes some time, okay, from here to here, definitely, okay. You leave a cup of ice on the table, it will take some time before you reach up to room temperature. So what you have over your right is called a heating curve. If you want to plot this heating curve, the y-axis is T degrees C. Be sure you label your axis. And time T measured as in second. Right? So initially, my temperature over my left is, I say that's what, 4 degrees, is it? No, negative 10. Okay? So initially it will be negative 10 at negative 10 degrees C. Then the temperature increase. This is where you have, oh, I have my 0. So therefore my 0 are not supposed to be here. So, okay, no more 0 here. Then what happened, if you have this experiment, you should do it. Stop for a while. It would definitely stop for a while before temperature start to increase. Okay, and this is where I have my 30 degrees C. And then what happened if I heat it up further, very long time until you get, depending on what is it, boiling or what boiling temperature. Okay, so this is basically what happened. This is the scenario. 60 degree, you heat up further. Depending on what's final temperature you want it. You see vaporization. Not that I don't heat it, I heat it up with okay. Okay, I heat it up, then vaporization. But from here to here it will take some time. Okay, so this is what happened. Something that you need to know and understand and pay attention would be here, right? From negative 5, from negative 10 up to 0 degree, this period of time is in solid, definitely solid. Okay, what do you call this period of time? Is we call it as heating. We call it heating. Heating followed by when the temperature do not increase. Okay, this is what you call it as fusion. Okay, this one here, the melting starts here, and here would be where the melting stops. Okay, now this part, this portion is what I call it as I mentioned, where involve energy used to melt it, energy used to break the intramolecular bond is m times L. Okay, now previously we have Q. Now I don't straight away go to Q yet. Q is energy. From the definition, specific latent heat. L is amount of energy used to raise 1 kg of mass at constant temperature. So this is what it means by that. So therefore, the heat required to break the intramolecular bond would be ml. Okay? Unit will be in joule. Okay? Right? So this is the time they define it as the fusion time. Okay? This is a time they call fusion. Fu. Okay? Fusion time. Then temperature start to increase. This is where you have your mc theta. Okay, mc theta is the kinetic energy. This is where the half mv squared kinetic energy of the molecule increases. Therefore, temperature increase. You may use the Q equal mc theta. Okay, where Q equals to mc theta. When temperature start to increase, there's change temperature. You use this equation. And what happened here would be definitely liquid. What happened when it reach up to this point, 30 degrees start to I wouldn't say it will start to freeze, but no, something's not right, because how can it start to be stable? Well, okay, the energy used is not to use to boil it, but sufficiently to maintain at 30 degrees at room temperature. Okay, until a point where you increase the heat. It's very, very confusing if I do it that way. So I change the temperature to maybe provide temperature sufficiently high so that it will heat up till 100 degree, because standard, because that's where you see a change in phase. 100 degrees C, okay, and this moment you call it as the boiling point. Okay, this is the boiling starts. You may increase it, the temperature would increase eventually. This is where the boiling stop or ends. Okay, this is where you successfully break all the intramolecular band. Liquid gas phase change to gas phase. Okay, so beyond this point, it will be a gaseous form. Here will be combination liquid plus gas. Between it will be solid and liquid. Okay, combination. So you find that a few information here would be the time over here to here. This is called vaporization. Now, the duration vaporization are supposed to be greater than fusion. Okay, the time for vaporization, V stands for vaporization, should be greater than the time for fusion, F, fusion. Why? Because here you need longer time. Why you need longer time? Because you need to break all the bonding. You need to change all the liquid bonding to the gaseous form. So that's why time here, one of the reason time is longer. Okay, so this is a heating because temperature start increasing. Okay, here temperature increases, so the kinetic energy gain kinetic energy, and therefore the molecule gaining kinetic energy, therefore the temperature increases. Here is flat, okay, meaning that energy is used to break all the intramolecular bonding so that it will change the phase from here it will be a liquid to gaseous. Okay, here another reason, okay, maybe you jot it down. Why is it longer? One is because um, more energy, okay, more energy more energy more energy used by liquid um, to change used by liquid energy used by liquid phase to fully breaks all not intra molecular bond for water. That's why it's longer. Another reason to it would be you find that the latent heat, okay, latent heat for vaporization is greater because more energy is required. Okay. Then one last reason would be why is it longer? Now, from liquid to gas, what happened? You have learned in chapter 3. You have pressure, atmospheric pressure. Here, all the liquid stay near the surface of water will be pressed against by the atmospheric pressure. The total amount of mass above it is high. So in order to overcome that, you need more energy to overcome that energy, overcome the external atmospheric pressure. Okay, why? Because to overcome the greater, because energy is required to overcome the external atmospheric pressure. Okay, I mean energy. Okay, extra energy. Okay, extra energy to overcome the external atmospheric pressure. That's why in vaporization you need the time is longer. Whereas here what happened is shorter period. Okay, so because from solid to liquid there's no external pressure, and the external pressure externally is low. That's why the time is shorter. Okay, so this is basically how you interpret it, how you understand this chapter better. By first you have the diagram. I mean a scenario. Okay, maybe this is 100 degree already. Okay, then you have vaporization. Right. The same is true, but I believe you were able to read through it from your reference for cooling curve. Okay, meaning from up here, what is temperature? Gas is cool, heat released to the surrounding. Yeah, cooling down, right? So cooling down would be heat released to surrounding, meaning heat loss surrounding. Therefore, the molecule, the kinetic energy of molecule decrease. When the molecule or the kinetic energy of molecule decrease, the temperature decrease. So from here to here decrease. Okay, then you have from down, and then you will flat, right? Okay, for water you will flat, then begin to condense into liquid, begin to condense liquid, meaning temperature remain constant. Latent heat of the vaporization released to the surrounding. Okay. Latent heat of vaporization released to the surrounding. That's why it's flat, actually flat because it takes time to form bonding. But you form bonding meaning when a bond is formed, what happens when two bonds comes together, then there's a release of energy, the release of heat. That release of heat you define as the latent heat of vaporization. Then average kinetic energy reducing, meaning therefore temperature keep falling. So you need to relate kinetic energy to temperature. So this is what I mean by that. Okay. So heating and cooling the opposite way, but yet you still need to read on your reference and text. Otherwise, it's very hard for you to already understand it. So let me give an example. Yeah, the scenario you need to choose from question. Maybe initially it says it's -5 degrees C. Heat it up, temperature increase up to 0 degrees C. Then at 0 degrees C, take some time. Okay, here. Then temperature raise 0 degree to room temperature. Okay. Oh, it's just a question. Doesn't need to memorize this. You just understand from here, and then apply according to the question that you have faced. An objective question. Yeah, so 0 degree, -5 to 30 degrees. So from your variation from here would be initially. Normally, the question says, "Oh, what's the energy required to raise the temperature of the ice from -5 degree up to a final temperature?" I don't know what is it, but for here it's 30 degrees. So how you will use it? First of all, you need to find out what are the energy involved. Right? So here to here, there's an increase of temperature, isn't it? Increase of temperature, therefore Q would be mc theta. You find out what are the value. Key in. C is the water. Okay? So definitely the temperature is 5. Then here, 0 degree, stay for a while. Okay, from here to here. Okay, this point. What happened here? Energy Q equals to mL. This is important. This is crucial. Normally, student tends to forget. I mean, this is 1 energy, 2 energy. Then from 0 degree to the final temperature. So this is an increase of temperature. So therefore, your Q3 would be mc theta. So here 0 to 30 would be 30. So the total energy would therefore be Q total would therefore be Q1 plus Q2 plus Q3. Unit is in joule. Number without unit, meaningless, right? And now there's some way in writing temperature. Okay, degree C. This is to tell the degree of hotness. C degree, it means means the difference of temperature. Okay, so 27 degrees C, it means the degree of hotness. It tells degree of hotness. Degree of hotness. How hot is it? How much of kinetic energy possessed by that liquid? Whereas Celsius degree, how you put this degree is a matter. Okay, after the C means different of temperature. Let's say from 0 to 30. So 30 C degree, meaning the difference of temperature is by 30 Celsius degree. Okay, the difference of temperature is 30 centigrade degree. Okay, be sure you know how and when to use what. It matters. Okay, it matters. Okay, degree of hotness. Celsius degree means the changes of temperature. Okay, well, that's all for me. I will not be able to cover. I thought initially I will be able to cover. This is what I mentioned earlier. I will not be able to cover the 3 law. I think I will make another video for the 3 law. I hope you like my video. press on thumbs up button. It will really inspire me a lot. And for you, if you are sitting for exam in the middle of midnight, you have just read this video. Go through this video. What you do is in the future, 1 week, 7 days, okay, or maybe 2 weeks maximum, okay, 1 week to 2 weeks, maximum 2 weeks, okay. Read whatever relates to this video from your reference. You should have at least 2 reference texts or 2 reference book from different brand. Read through it, experiment, set out experiment, application, and try the objective questions in a week time or 2 before you proceed to my next video. With that, thank you for watching. Stay tuned to my next video.